I have a problem that's related to Gauss's pretty well-known Eureka problem, where it states that any integer can be written as the sum of 3 squares, I believe. Now, this triangle of dots that I have right here has 10 dots. You can count them, okay, given by this. Now, this is an unfactored way to write something that's a little more familiar to you guys as n times n plus 1 over 2. But notice there's 4 rows here. There's 4 rows in this triangle, and there are 10 dots. You can count them. And there's 4 squared plus 4 divided by 2 equals 10 dots. Okay, 10 dots in this triangle. Now, we're going to use this fact to show that if S is the sum of 3 triangular numbers, that 8S plus 3 is the sum of 3 odd squares. And again, this is kind of a strange wording. I like it better than what I've seen in some problem number theory textbooks. But based on what I just showed you, we can write S this way, okay? 3 different integers, case of 1, case of 2, case of 3, is in this form that you see up here, 4 squared plus 4 over 2 is equal to 10. Okay, so we start with that, and then we do a little bit of algebra, and the algebra is a little, shall we call it unmotivated, but we're trying to make it we're trying to get it in a form where we can recognize 8S plus 3 is the sum of 3 odd squares, okay? So if you multiply by 4, you're getting closer, and then if you complete the square, it's a key step that's not explained a lot of times. People just say we completed the square, but here's the work. As usual, you take half of the coefficient of the linear term and square it, which gives you 1/4. Okay, now at this stage, if you multiply through by 4 again, you get 8S plus 3 like we want it. And you have this, I wrote 4 as 2 squared, and that's because we can now write this as equal to, this is properties of exponents right here, 2 case of 1 plus 1 squared, and so on. Okay, and again, you can see that is just laws of exponents. Now we have 2 case of 2 plus 1 quantity squared. And finally, 2 case of 3. Whoops, I wrote that wrong over there. I'll change that. 2 case of 3 plus 1 quantity squared. Okay, let me fix this. Erase him. See if I can do that. I don't even know if I can. Okay, y'all, that doesn't work. But anyway, there's supposed to be a 2 right there. That should be a 2K. I don't know how to erase it from here. I don't want to screw around with it any further. But anyway, this is the sum of, this is a mistake right here. 2 should be in front of the case of 2. But in any event, we've proved it. And again, this looks like a very strange problem, but it is related to a fairly famous problem that Gauss solved when he's a teenager, like in 1796, where you can take an arbitrary integer and write it as the sum of 3 squares. This is very specific, but apparently this, and I haven't proved it myself, is equivalent to that. I'm not sure if that's even true. But in any event, I guess that does it, folks. And again, this 2 should be inside as a coefficient of case of 2. Good day.